Welcome back. In this section, we'll be introducing exponential functions, and we'll also be looking at some applications of exponential functions. So first, to begin with, when I say an exponential function, I mean a function that has this form. Some constant times some other constant to a power where the power is our variable x. So this is a little bit different than the polynomial functions where x was the base and we might have had a power of 2 or a power of 3 on the x. Here, for an exponential function, x is not the base, x is the power. So here, the base of our function is going to remain a constant. Our base is always a, and that it's our power that changes. A couple of things just to mention here about our base. Uh, while we're allowed to have whatever number we'd like for our constant c, provided that it's not 0, because of course if c was 0, then f of x would just be 0, and of course that's not really an exponential function, that's a constant function. But for a, we have a restriction, and the restriction that we have is that number one, a, our base, needs to be positive, and also our base cannot be 1. The reason we're restricting 1 from our base would be that if you had a base of 1, then you'd be talking about a function that was some constant times 1 to the power of x. And 1 to any power is always equal to 1. So really, again, if a was 1, we'd be talking just about a constant function. And of course, we don't want to have that. So we don't want a to be 1 because that would give us a constant function. We don't want c to be 0 because, again, that would give us a constant function. And the other restriction that a is positive is because otherwise, if we had a base that were negative, then there would be many instances where the exponential function wouldn't be a real number. And the example that I have here is this. If you had a base of negative 5, then negative 5, for example, to the power of a half, we know that that's not a real number because that would be square root of negative 5. So that means that f of x, if you did allow the exponential function to have a base that was negative, would have values where f of x is not a real number. And of course, that would also be true for fourth roots, which would be if x were a quarter, sixth roots, if x were a sixth, and so on. There'd be, in fact, infinitely many different values of x where an exponential function would not give you a real value. So to prevent that, we're going to only restrict ourselves to positive bases. And so that's something that I want us to keep in mind for the rest of this course, that when I'm talking about an exponential function, and also later on when I introduce logarithms, that for both, the base needs to be positive and cannot be 1. Okay, so let's just do this here. I've got something f of x 5 to the power of 3 minus 2x, and I just want to rewrite it in that exponential form, constant times some constant to a power of x. And of course, I could do that just using my exponential rules, my rules of exponential expressions. I have 5 to the power of 3 minus 2x, so we know that that's 5 to the power of 3 times 5 to the power of negative 2x. That's just using one of our rules for exponents. And then after that, we also can say, well, 5 to the power of 3, that's just a number. That's 125. So we're almost at where we want to be. We want it to be some constant times some base to a power of x. We've got a constant, we have a base. It's not raised to a power of x, though, yet. It's raised to the power of negative 2x. But again, we can use the exponential properties that we know to fix that. Because if you're thinking about 5 to the power of negative 2x, you could think of that as 5 to the power of negative 2 to the power of x. Because remember that when we're multiplying, when we're taking an exponential expression and raising it to a power, when we have a power raised to a power, we multiply those powers together. So when you have 5 to the negative 2x, that is 5 to the negative 2 raised to the power of x. So I'll just continue on over here. 5 to the power of negative 2, that's 1 over 5 squared. That's 1/25th. And then there we go. So we were able to rewrite it in that exponential form. So here our constant c, that's 125, and our base is 1/25th. All right, so now another one that we want to do here, we have an exponential function that is supposed to pass through these points, 1, 3, and 2, 18. And we know that the basic form for the exponential function would be some constant times a to the power of x. Now, we know that it has these 2 points that are on it, which means that that equation has to be satisfied for the point 1, 3 and also the point 2, 18. So in other words, if you were to put in 1 for x, you would get 3 for y. If you were to put in 2 for x, you should get 18 for y. And so from the 2 points, we have 2 equations with 2 unknowns, and it's going to be easy enough for us to solve for what a and c need to be. I'm just going to label this as equation 1 and equation 2. So I'm going to start with taking equation 1 and rewriting it. Equation 1 tells me that 3 equals c times a, but of course I could rewrite that as 3 divided by a equals c. And I know that it's fine for me to divide by a because remember, a, our base, needs to be positive. It can't be 0, so there's no concern that I might be dividing by 0 here. I know that a is not 0, so I certainly am not. And then now we'll continue on. I'll substitute this into equation 2. So in equation 2, I had 18 equals c times a squared, and c, we said, was 3 divided by a. And so now at this point, all I need to do really is just simplify this. I have on the right-hand side 3 divided by a times a squared, that the a and one of the a's here will cancel. So you would have that 18 is equal to 3 times a, and from that you can find out that a should be 6. Once we know what a needs to be, then we can use what we have over here, that c is supposed to be 3 divided by a. So using that, we can say, well, c is supposed to be then 3 divided by 6, or a half. So that means that our exponential function that we're looking for should have that constant in front of a half, and that the base for our exponential function is 6. So there we go. Our exponential function, the one that we're looking for, should be 1/2 times 6 to the power of x. So one of the applications that we have for exponential functions would be compound interest. So just a little bit about banks and banking. Banks pay you money when you deposit money in your account and you leave it there. The money that you deposit in your account, we call that the principal. Usually we use the capital letter P to represent our principal. So P dollars we deposit into our account. And then every month or every week or every year, depending on how often the money is compounded, how often you get the interest calculated and paid, the bank will calculate a percentage of the amount of money that you have in your account and pay that amount to you to increase the amount of money that you currently have in your account. There's 2 kinds of interest. There's simple interest, where the interest is only calculated based on the principal. So if you have, for example, $100 in the account and you're getting 10% interest, simple interest every year, then every year the bank would pay you 10% of that $100. Every year the bank would give you $10. You would have, after the first year, $110, then after the second year, $120, then $130, and then $140, and so on. Now, if the interest is compound interest, which is usually what's given at banks, then the interest is not just calculated on what you deposited, it's calculated based on what you've deposited and also any interest that they've previously paid out. So, for example, again, if you're thinking about that $100 that you deposit with 10% interest, and again, let's pretend that this is interest being charged and paid once a year, then at the end of the first year, you'd get 10% of that $100. You would have $110 in your bank account. But after the second year, they would give you 10% of the $110. You would get $11 worth of interest. So after the second year, you'd have $121. And then the next year, they'd pay you 10% of that. They'd pay you 10% of 121, which would be $12.10. So the following year after that, you'd have $133.10 in your bank account. So notice that for simple interest, as I said, every year it would be going up by 10. You'd have $110, then 120, then 130. But for compound interest, we're gaining a little bit extra because we're earning interest on top of our interest. So the formula that we use to calculate this compound interest is this, where A is the amount of money that we'll have in our account, P is our principal, the amount that we've deposited, R, this is the stated rate, this is the rate of interest that the bank says that they're going to pay per year, and N, this is the number of times per year that you receive that interest. And then finally, T, this is the number of years that you leave the money in your account. One thing I do want to clarify, and because you might be wondering in this formula, why are we taking the interest rate and why are we dividing it by how many times per year you get the interest? And the reason for that is this. When the bank tells you how much interest they're giving you, the stated rate is how much you're getting per year. So they might say, we will pay you 12% interest annually. But then when they tell you how often it's compounded, that's telling you how that 12% will be split up. So for example, if they're giving you 12% and they're compounding it only annually, then you'll get that 12% all in one piece. But if they give you interest monthly, they're not going to be giving you 12% every month. They're going to be giving you 1% every month, and that over an entire year would add up to the 12%. So just a couple of common ways that you might have your interest compounded. Commonly might be compounded annually, so once per year, or semi-annually, twice per year, every 6 months. Quarterly, fairly common, 4 times a year, or monthly, or daily. And of course, it could be compounded otherwise. It could be compounded weekly, in which case there would be n equals 52. There would be 52 compounding periods in a year. One little thing that I want to just mention here is that for this course, we're not going to worry about the fine distinction of what if there's a leap year that year. If this was some sort of financial mathematics class where we were really interested in calculating compound interest, then we'd look into how would the banks calculate their compound interest in the case of leap years versus non-leap years. But for us, for this class, if I say compounded daily, then we're going to just assume that every year always has 365 days. We're not going to worry about a 366 days. What if we have a leap year? That's not going to be something that we're going to worry about. But do keep in mind, though, for banks, actual banks, they do that calculation taking care of the leap year. Anyhow, let's continue on and do some examples. Okay, so for this one, we have the start being that we're depositing $1,000 into an account that's paying an annual interest rate of 4% compounded monthly. So some things that we can see right at the very beginning of this. Number one, I'm depositing $1,000. So that's telling me that my principal is 1,000. I also know that I have an annual interest rate of 4%. I also know that R is 0.04. This is something just to mention here before we go further, that although in everyday language we speak about percentages like 4% or 10%, when we write percentages, we express them as decimals. So I'm not going to say that R is 4, even though it's an interest rate of 4%. I should be saying that R is 0.04. And then finally, here we are also told that this interest is being compounded monthly. So we're being told that N is 12. Number of times we'll get interest will be 12 times per year. And we also want to know how much will be in the account. So what we want to know is, what is A, the amount of money that will be in the account after 5 years. So if it's after 5 years, then that means that T, the number of years that we're leaving the money in the account, is 5. One thing to also be careful here for our calculations, T that we have for our formula for compound interest is being measured in years. So if somebody were interested in leaving their money in the bank for 6 months, let's say, then you would say that T is 1/2, because 6 months would be 1/2 of a year. Okay, so now we are pretty much ready to go. We just need to write down our formula, put in what we have, and then calculate what we get. Our formula is A is equal to P times 1 plus R over N to the power of N times T. And we've got all of those things. We have P is 1,000, R is 0.04, N is 12, and T is 5. For the power that we have here, we have N times T, which would be 12 times 5, and that is 60. So now I just need to run that through my calculator. 1,000 times 1 plus 0.04 divide by 12, close bracket, to the power of 60. And when I ran that through my calculator, I got 1,220.996. Now, of course, since we're talking about money amounts, then we should really be rounding our answer off to 2 decimal places. So here when I'm going to give my answer, I'll round it off to 2 decimal places. And since this is a word problem, I should also be giving my answer in terms of a sentence. So I'm not just going to stop here and say 1,220.996. I'll say that after 5 years, there will be $1,221.00 in the account. There we go. So that, I can say, is my final answer to this question of how much money will there be in the account. The answer will be $1,221.00. If I round it to 2 decimal places, there we go. That's how much I'll have. So that kind of turned out nice. No cents left over, just nice whole number amounts. So that means that since we deposited $1,000, and since we have 1,221, then over those 5 years, we've earned $221 in interest. Okay, so one more here. We've got a bank account and it pays an annual interest rate of 2%. So we already know that R is 0.02. It's compounded quarterly, so we know that N is 4. We want to know how much should I deposit now. We want to know what is the principal. Remember, principal is the amount that we deposit now, and the amount A, that's our final amount that we'll have after, in this case, 10 years. So we know that T is 10, and we want our final amount of money to be 5,000. So now here we're looking for how much do I need to deposit now? What would my principal be to have my final amount A be 5,000? And so again, we're using the same formula. We have that our final amount is principal times 1 plus r over n to the power of n times t. We know our final amount, that's 5,000. We know what r is, it's 2%. We know what n is, that's 4. And the power here would be n times t, 4 times 10, or 40. And so now I just need to solve for p, and so what I'll do is I'll take this equation and divide both sides by that expression. So I'll have that p is equal to 5,000 divided by all of that, 1 plus 0.02 divided by 4 to the power of 40. And then when I ran that through my calculator, I got about 4095.694, which makes sense. I mean, if we're thinking about this, we're wondering how much money should I deposit now so that I'll have $5,000 in 10 years. So the amount I deposit now should be less than 5,000 because 5,000 will be my final amount, and the amount I put now should be less than that. So that makes sense. I can say here then I should deposit $4,095.69. So that's my answer then for how much money should I deposit now. And if you did that, if that were the bank account that you had, then putting in that $4,095.69 now means that you will have $5,000 in your account after 10 years. Okay, one last before we take a break. Here we've got a couple of things. We have a $500 deposit and we want it to double in value in 5 years. So that's telling us, number one, that our principal is 500 and that we want our amount to double in 5 years, so we want our final amount to then be 1,000. And the question we have is, what would be the interest rate compounded monthly that I would need to receive in order to make this happen? Well, we want it to double in 5 years, so t needs to be 5. We don't know what the annual interest rate is, r. R is the mystery, that's what we're looking for. But we do know that it's going to be compounded monthly. We do know that n is supposed to be 12 times per year. So let's put together what we have. We know that our final amount is our principal times 1 plus r over n to the power of n times t. And we'll put in what we have. Our final amount is 1,000. Our principal is 500. Our rate we don't know, but n happens to be 12. And then for that power, n times t, that's 5 times 12, that would be 60. Okay, so now I just need to solve this for r. First thing that I'll do is I'm going to divide both sides of this equation by 500. So when I do that, on the left side I'll have 2, and on the right side I'll just have that 1 plus r over 12 to the power of 60. Okay, so I'd like to solve for this, and so what I'll be doing is I'll be then taking the 60th root, because of course if this were a square, you would take a square root. If it was cube, you would take a cube root. Since this is the power of 60, I'll take the 60th root, but instead of me writing it as 60th root of 2, I'm going to write it as an exponent. Remember that the 60th root would be the power of 1/60th. That makes a nicer looking way to write things down. So we have 2 to the power of 1/60th equals 1 plus r over 12. And now we just have to continue solving for r. So let's move the 1 to the other side. and then multiply both sides of this equation by 12. And then we just need to find out what r is here, and I find that r is approximately 0.1394. So that means, as far as what interest rate do I need an interest rate of 13.94%. Now, there is one moment here where we maybe should be a little bit critical of what we did, which is this. If we're thinking about this step here that we did when we took our root, hopefully somebody who's watching this video is thinking, well, if this was a square, we would have taken plus or minus the square root. Since that's an even root, why didn't we take plus or minus the 60th root? And so it's a good question to bring up, and it's a good question to think about, because if this wasn't something that was part of a word problem, if this was just an equation that we were trying to solve, then you would be right. We would be thinking of taking plus or minus the 60th root. The reason that I didn't take plus or minus the 60th root here is because I know in advance that since I'm talking about things where r is an interest rate, then interest rates are percentages. Those are numbers between 0 and 1. So that's the reason why I shouldn't have a negative here. If I had a negative 60th root of 2, that could make the final outcome that I have here a negative value. And of course, that would mean you'd have a negative interest rate, and that's not what banks do when they're paying you interest. The interest rate is a number between 0 and 1, so that's the reason, in case you're wondering why didn't I do plus or minus, because I knew in this case the interest rate must be positive, so there couldn't be a negative 60th root of 2 in my calculations. So for me, for this, if I want my money to double in 5 years, I need my interest rate to be 13.94%.